Hey there, and welcome to this explainer. Grab a seat and let's just imagine we're sitting down in my office for a one-on-one mentorship session. Look, if you're an engineering student right now staring down your career roadmap, trying to figure out exactly where to specialize in a world that's changing at lightning speed, you are definitely in the right place. Today, we're going to map out your future. We're specifically diving into the massive shift between traditional mechanical engineering and the absolutely booming field of smart manufacturing. Because, let's be real, the decisions you make right now, they're going to define your whole trajectory for the 2026 job market and way beyond. So, let's get right into it.
Here's a quick look at our agenda for today. We'll start with the big picture, the manufacturing evolution. Then, we'll figure out how to choose your specific engineering path, take a hard look inside the actual course syllabus, and see what all of this looks like in the real world. Finally, we'll cover global careers and salaries, and wrap things up with my final mentor advice.
All right, Section 1, the manufacturing evolution. Moving from isolated machines to thinking factories.
Now, to really understand where your career is headed, you have to understand the massive macro shift that is Industry 4.0. In an old-school traditional factory, your job is mostly about process improvement and just keeping stable systems running. The machines out on the floor, they act like isolated islands of automation. When something breaks down, humans have to go out and diagnose it. But in a smart factory, it's a whole different ballgame. You're dealing with connected cyber-physical systems and data-driven decision-making. Instead of just asking, hey, what's happening on the line right now, a smart manufacturing engineer asks, what does the data say is about to happen? You're building systems with predictive analytics to track defects and stop failures before they even have a chance to occur.
And you might be wondering, what's driving this fundamental shift? Pure economic demand. $65 billion. That is the projected value of the global robotics market by the year 2030. It's a staggering number, right? This sheer unprecedented demand pretty much guarantees that engineers who actually understand these interconnected, automated systems are going to be the absolute most sought-after talent on the planet.
Moving on to Section 2, choosing your engineering path. Let's break down mechanical, mechatronics, and smart manufacturing.
With all this rapid change, honestly, you might be a bit confused about which major to even declare. So let's define your potential roles here. Traditional mechanical engineering is focused heavily on physical structures. Think thermodynamics aimed at sheer physical reliability. Then you have mechatronics, which blends electronics and mechanics to create intelligent devices. But if you jump into smart manufacturing, your focus zooms way out to integrated, data-driven factory ecosystems. Here's the easiest way to think about it. A mechatronics engineer designs the physical robotic arm itself, but the smart manufacturing engineer, they design the entire digital ecosystem that the robot talks to, connecting it to the supply chain, the quality control sensors, and the cloud. You're the one making the whole orchestra play together.
Okay, Section 3, inside the course syllabus. Time to build your skill stack. Now, if you do choose the smart manufacturing path, you don't just jump straight into AI on day one. You've got to build that physical engineering intuition first. Top institutions all over the globe are standardizing these super rigorous curriculums to make absolutely sure you speak the language of traditional mechanics fluently while simultaneously mastering the digital tools of the future.
Let's map out how this builds year by year. In your second year, you're really grounding yourself in the fundamentals, like thermodynamics, sure, but you're also taking embedded systems to learn how to actually harvest data from those physical machines. Then, in your third year, you shift over to systems integration. You're studying industrial robotics, advanced CAD/CAM, and metrology, where you figure out how to use sensors for real-time quality control. And by your fourth year, you are right on the cutting edge. Additive manufacturing, industrial IoT, and digital twins. You literally shift from learning about individual gears to optimizing entire cyber-physical ecosystems. It's awesome.
Next up, Section 4, real-world smart manufacturing. Let's look at Industry 4.0 in action.
So imagine you've graduated. What does your daily work actually look like on the floor? Well, it heavily revolves around concepts like the digital twin. Basically, this is a super high-fidelity virtual replica of a physical asset. Mastering this is what empowers you to test, simulate, and optimize entire production lines entirely digitally. Let's say you want to speed up a massive conveyor system. Instead of walking out onto the factory floor and physically tweaking the machines, which risks millions of dollars in downtime if you mess up, you simulate the whole thing on the digital twin first. This, right here, is exactly how data-driven roles operate.
Let's ground this with some heavy hitters. Take Rolls-Royce, for instance. They use smart manufacturing for predictive maintenance in their aerospace engines, analyzing real-time data to literally fix parts right before they fail. Mind-blowing, right?
Apple relies on advanced manufacturing engineers to design these ultra-high-precision automated assembly lines that can pump out iPhones with zero margin for error. And Tesla uses smart systems to automatically reconfigure their EV lines. That means a single assembly line can seamlessly adapt to produce totally different vehicle variants back to back. If you go this route, these kinds of automated, data-centric workflows, that's what will dictate your daily responsibilities.
All right, let's talk numbers. Section 5, Global Careers and Salaries, the ROI of your degree.
Because you're successfully bridging that tricky gap between mechanical hardware and digital software, your skill set is incredibly unique. You're basically a unicorn, and the global market pays a massive premium for it. Over in the United States, we're looking at mid to senior salaries hovering right around $150,000 for experienced roles. Germany, which is basically the engineering powerhouse of Europe, offers equivalents around $90,000, and Japan is sitting around $60,000 to $90,000 depending on your exact specialization. Your ability to integrate software expertise with deep mechanical knowledge is highly valued pretty much everywhere on Earth.
And for those of you looking at the domestic market in India, the placement records at premier institutions right now are honestly staggering. Entry-level roles like an automation engineer are starting anywhere between 6.5 and 15 lakhs. But for that top percentile, people in specialized R&D and system integrator roles, they are securing packages exceeding 50 lakhs. Companies are absolutely desperate for professionals who can actually execute digital transformation on the ground, not just talk about it. Furthermore, your opportunities aren't just boxed into one sector. You are highly sought after in automotive, semiconductors, aerospace, and even major tech consulting firms like Accenture that advise clients on Industry 4.0. And if you're dreaming of working abroad, this degree offers incredible global mobility. We're talking clear, established pathways to secure visas like the EU Blue Card in Germany or the Employment Pass in Singapore. Finally, Section 6, the mentor's final advice, real student experiences, and your next steps. Now, before we wrap up, I want to ground this mentorship session with some completely candid, realistic advice drawn directly from actual engineering students. I want you to know exactly what you're signing up for. This review right here hits the nail on the head. You are studying electronics, computer science, and mechanical engineering all at once. The workload is heavy, really heavy. So my advice is this. Only take this path if you have a genuine, burning interest in mixing these disciplines. If you just want to turn wrenches, stick to traditional mechanical. But if you want to write the code for the system that turns the wrenches, this is absolutely for you.
So, what's the game plan? Here is your 3-step action plan to completely dominate the 2026 job market. Step 1. You must master the physical, mechanical fundamentals first. You simply can't optimize a machine if you don't understand how it physically works in the real world. Step 2. Learn the digital thread. Get super comfortable with IoT, data analytics, and programming. And Step 3. Secure targeted certifications. You gotta go outside your core classes. Get certified in cloud computing, cybersecurity, or data visualization tools like Power BI. This combination right here, it makes you basically unstoppable.
And that brings us to the end of our explainer. But I'm going to leave you with one big provocative question to chew on tonight. When you look down the road at your future career, are you ready to just solve process problems, or do you want to solve process and technology problems? Because let me tell you, manufacturing is becoming a tech industry, whether people are ready to admit it or not. Decide what kind of impact you want to make and let that guide your choice. Thank you so much for joining me for this mentorship session, and I'll catch you in the next explainer.